Before I started my thesis research, I instinctively thought of soil as a static thing. It's soil, it's dirt, it's a medium that provides for other things to grow. Of course, while Earth's land based ecosystems are directly supported by soil, soil itself is one of the most complex and critically important environments on Earth. A single gram of soil, so maybe a quarter teaspoon's worth, can contain over 100 million bacterial cells. These bacteria, in addition to being rich sources of antibiotics and pharmaceuticals, also help lock away 3 times the amount of carbon that's in the atmosphere, making soils a critical reservoir to consider in global warming dynamics. Unfortunately, soils are being lost to erosion about 10 times faster than they can form. Thus, understanding the processes of soil formation is critically important to help mitigate their loss. Maybe one day we can even make our own soils and help support agriculture in traditionally non-farmable environments. This is the motivating question behind my research. How do soils form, and can we use this knowledge to generate our own soils? Soil formation typically begins with the weathering of a parent rock, producing smaller rock fragments and slowly dissolving the minerals that make up the original material. This produces free elements such as calcium, magnesium, and silicon, which can then either be washed out of the system completely or recombined to form the clay minerals that are so hugely important for soil health and longevity. This process of mineral dissolution and clay formation can be accelerated or slowed down by many soil-dwelling microbes. One class of bacteria in particular, the Ctedonobacteria, are often found in very high abundance in young or early forming soils, suggesting that they play a role in the soil generation process. As you can see, Ctedonobacteria have somewhat of a vine-like structure carrying grape or raisin-like spores, which help them both attach to mineral surfaces and survive a complex and changing environment. As part of my research, I grow Ctedonobacteria on rock chips and directly measure elements as they're released from the parent rock over time. I also use small fluorescent probes and microscopy to visually track the flow of these elements as they dissolve from the parent rock. Preliminary results indicate that some Ctedonobacteria may actually slow mineral dissolution in some cases, which could lead to long-term soil chemical stability. At the conclusion of my research, I hope to show how Ctedonobacteria fundamentally interact with their geologic environment, which at the time is not presently known and could have huge implications for soil formation. Thank you.